In this research, the authors explore the potential of combining representation learning and exploration in long-horizon reinforcement learning tasks. They hypothesize that using the same dataset to learn both representations and auxiliary rewards can lead to improved sample efficiency and performance. The paper focuses on the challenging NetHack benchmark, a terminal-based roguelike video game that has proven difficult for both humans and AI agents to solve. The authors first discuss the challenges in sequential decision-making tasks, such as sparse reward signals, large policy spaces, and long task horizons. They then delve into auxiliary tasks in reinforcement learning, which can be used to augment the primary goal of maximizing expected reward. These auxiliary tasks can provide desirable inductive biases for the agent, enhancing its ability to solve complex problems. The paper also reviews various methods for learning from demonstrations, including classical imitation learning techniques like behavior cloning and Gale. These approaches leverage expert trajectories to guide the agent's learning process, improving its performance in domains where it struggles to achieve human-level proficiency. The authors propose a novel approach that utilizes offline pre-training to accelerate exploration and representation learning. By learning a state representation using noise-contrastive estimation and a model of auxiliary reward from a single collection of human demonstrations, they demonstrate significant improvements in sample efficiency and base performance on the NetHack benchmark. This is achieved by pre-training the agent on offline data, which can then be fine-tuned online. The proposed method combines the strengths of both representation learning and exploration strategies, enhancing the agent's ability to prioritize tasks effectively and capture crucial environmental parameters. This work contributes to bridging the performance gap between reinforcement learning agents and humans in challenging domains, illustrating the potential of leveraging offline data for improving exploration and representation learning in long-horizon tasks. In the realm of reinforcement learning, solving long-horizon problems with large action spaces and sparse rewards is challenging due to the need for an uninformed agent to try a vast number of actions. To address this issue, the Explore Like Experts (ELE) algorithm utilizes expert human demonstrations to guide exploration. ELE first trains a progress model G(S)R by minimizing the mean squared error regression in signed log space to predict time offsets from states. This model is then used as a heuristic in the auxiliary MDPM0, where the reward function combines the extrinsic reward with the progress model, effectively lowering the discount factor in M0. The conditional probability distribution of future states given the current state can be efficiently estimated using an implicit model F(S)R trained via contrastive learning on offline demonstrations. At optimality, F approximates the future state visitation probability under the optimal policy, up to a multiplicative term. This methodology is detailed in the paper's section on methodology, which also describes how to use the same offline data for training progress models and ELE's progress model. The pre-training phase of state representations with contrastive training aims to learn fundamental inductive biases required for exploration from existing demonstrations, such as state connectivity structure, action effects, perceptual local invariance, and sequential dependence of states. This improves the sample efficiency of the agent during the online phase. The paper further elaborates on the use of these state representations in Muesli, a strong reinforcement learning baseline. This paper presents a novel approach to accelerating exploration and representation learning in reinforcement learning tasks using offline pre-training. The proposed method combines contrastive pre-training with online learning, leveraging the now top 10 dataset of human games from top 10 players on nethack.alt.org. This dataset provides a good balance of trajectory quality and diversity, making it ideal for pre-training state representations. The experimental setup involves comparing the performance of Muesli and ELE algorithms with and without pre-trained state representations on 7 different tasks from NetHack, ranging from dense to sparse rewards. These tasks include score, scout, depth N, level N, and oracle tasks, each posing unique challenges in terms of reward sparsity. The results show that equipping strong reinforcement learning algorithms like Muesli and ELE with human demonstrations via offline pre-training significantly improves the sample complexity of the underlying method. While ELE outperforms Muesli on the sparser tasks, The performance does not improve on the denser score and scout tasks, and in fact, is inferior to Muesli. However, using contrastive pre-training with both Muesli and ELE significantly improves its performance in the sample regime under investigation in this work. In addition to the main results, ablation studies are conducted for different components to understand the impact of each element on the overall performance. The findings suggest that the proposed approach can accelerate exploration and representation learning, leading to improved sample efficiency in various reinforcement learning tasks. The architecture used in this work is a residual network, ResNet, which encodes 80 by 24 TTY arrays with a series of 2D convolutional blocks. This model acts as an encoder used by contrastive pre-training, ELE's progress model, as well as the Muesli agent. During the online phase, the generated representation is passed through a recurrent network, LSTM, and an MLP to predict policy and value heads in Muesli. For contrastive pre-training, the ResNet encoder is passed through an MLP to project the state features into a latent space. Overall, the paper demonstrates the effectiveness of combining contrastive pre-training with online learning in reinforcement learning tasks, particularly in improving sample efficiency and accelerating exploration. The findings have implications for future research in representation learning and exploration strategies in reinforcement learning. Here is a combined summary of the 2 pages. The authors investigate the effectiveness of offline pre-training in accelerating exploration and representation learning in the context of imitation learning. They propose a method called ELE, which combines contrastive pre-training with an exploration bonus to learn a robust representation of the environment. The results in Figure 4 demonstrate that ELE outperforms standard imitation learning baselines, such as BCO, GAIFO, and FORM, on both sparse and dense tasks. The authors also analyze the importance of pre-training in representation learning by comparing the performance of ELE with and without pre-training. The results in Figure 5 show that pre-training significantly improves the performance of ELE, especially on sparse tasks. This suggests that pre-training captures a different dimension of exploration and representation learning. The ablation studies in Section 5.3 investigate the importance of using a separate encoder for pre-training, freezing pre-trained representations during the online phase, and the impact of encoder architecture on performance. The results show that using a separate encoder for pre-training is beneficial, and freezing pre-trained representations does not significantly affect performance. Additionally, the authors find that a ResNet architecture is better suited for contrastive pre-training than a vision transformer (VIT) architecture. The authors conclude that offline pre-training can be used to learn robust representations of the environment, which can be fine-tuned during the online phase to improve exploration and representation learning. They demonstrate the effectiveness of their approach in the challenging NetHack environment, which has a large state and action space, long task horizon, and strong notion of forward progress. The paper discusses the development of an offline pre-training method for reinforcement learning, which significantly accelerates exploration and representation learning. This approach leverages large amounts of unlabeled data collected from various sources, such as online videos or Wikipedia, to pre-train a model that can be fine-tuned for different reinforcement learning tasks. The authors demonstrate the effectiveness of their method by applying it to several Atari games and a 3D maze environment, achieving state-of-the-art performance in both settings. The proposed approach is based on the idea of using contrastive learning, where the model learns to differentiate between real and fake data. In the context of reinforcement learning, this translates to distinguishing between actual game states and randomly generated ones. This process allows the model to develop a robust representation of the environment that can be utilized in various tasks without requiring extensive exploration during the fine-tuning phase. The authors also explore different variants of their method, including the use of negative sampling, which further improves the performance of the pre-trained model. Additionally, they provide a detailed analysis of the factors contributing to the success of their approach, such as the importance of using a diverse set of pre-training data and the role of the contrastive loss function in shaping the learned representations. The paper concludes by discussing potential future directions for this line of research, including the integration of additional sources of unlabeled data and the development of more sophisticated exploration strategies. Overall, The proposed offline pre-training method offers a promising avenue for enhancing the efficiency and effectiveness of reinforcement learning algorithms, particularly in complex, high-dimensional environments where exploration is challenging. Here is the combined summary of pages 11 and 12. Recent advances in reinforcement learning have led to the development of various methods for accelerating exploration and representation learning. Offline pre-training has emerged as a promising approach, leveraging large datasets to improve the efficiency of subsequent online learning. Researchers have proposed several methods for offline pre-training, including behavioral cloning from observation, generative adversarial imitation, and contrastive representation learning. These methods have been applied to various domains, such as robotics, gameplaying, and sequential decision-making. To better understand the role of representation learning in offline pre-training, researchers have investigated the use of different distributional assumptions for modeling the relationships between states. For example, the contrastive pre-training scheme and the ELE progress model employ different distributions, including the truncated geometric distribution and the log uniform distribution. The choice of distribution has significant implications for the flexibility and efficiency of the approach. Experimental results have demonstrated the effectiveness of offline pre-training in accelerating exploration and representation learning. For instance, using a frozen pre-trained state representation in the online phase can lead to improved performance. Additionally, the use of a truncated geometric distribution for modeling state transitions has been shown to be advantageous. The algorithm for pre-training with online learning involves several key components, including the use of a contrastive loss function for pre-training the state embedding, a forward progress model for learning the relationships between states, and a policy update step for adapting the policy to the online environment. The pseudocode for the algorithm is provided in Algorithm 1. Experimental details, including the distribution of time offsets and computational resources, are also discussed. The results highlight the importance of carefully designing the pre-training procedure and selecting the appropriate distributional assumptions for modeling state transitions. The evaluation of the proposed approach's performance is presented in Figure 9, which displays the episode returns with and without freezing the representations of contrastive pre-training during the online phase. The results indicate that there is no significant difference in performance with or without freezing the representations of the encoder during online training for most tasks. Consequently, all other results are reported with the representations from the pre-training phase frozen. The implementation details of the approach are outlined in the appendix, with hyperparameters listed in Table 1. Notably, the contrastive discount is set to 0.95, and the batch size is 576 sequences. These hyperparameters differ from those used in ELE, Anonymous, 2023. While the architecture of the encoder remains the same as in ELE. Each experiment was run on 8 TPUV3 accelerators using a podracer configuration, Hessel et al., 2021b. The results suggest that the proposed approach can effectively accelerate exploration and representation learning through offline pre-training. The use of contrastive pre-training enables the learning of dense and sparse representations, which can be leveraged to improve performance in various tasks. The evaluation results demonstrate the efficacy of the approach, with performance comparable to or surpassing that of existing methods. The proposed approach builds upon the ELE framework, incorporating contrastive pre-training to enhance representation learning. The use of a sparse encoder architecture enables efficient exploration and learning in complex environments. The results highlight the importance of offline pre-training in improving performance and accelerating exploration. The evaluation protocol involves running experiments on 8 TPUV3 accelerators using a podracer configuration, ensuring efficient and scalable computation. The hyperparameters are carefully selected to balance exploration and exploitation, with the contrastive discount and batch size playing critical roles in shaping the learning process. The results presented in Figure 9 demonstrate the effectiveness of the proposed approach in accelerating exploration and representation learning. The use of contrastive pre-training and sparse encoder architecture enables efficient and scalable learning, with performance comparable to or surpassing that of existing methods.